Okay, so this lecture is on separation axioms, and we introduced the notion, the definition of a Hausdorff space, T2. So T2 means that we can separate 2 points, right? And we can push that forward, so we can require the space can separate something larger, i.e. sets, right? So here's the definition. So given let X fixed to be a T1 space, so T1 means that finite sets are closed, and we say that X is regular, so regular space is called T3, if for any element in X and for any closed set in X such that it does not contain X. So if this is X and this is B, right? It does not contain, then there exists U V open at X such that they're disjoint, and it separates X and B. And a stronger one is called normal. X is called the normal space. T4 is that for any 2 closed sets that is disjoint, then there exists 2 open sets such that they are disjoint. Open set they're disjoint and contains A and B. So it's like if you have A and you have B, they're disjoint, then there exists U and V, right? This separates them. So observation, T4 implies 3, T3 implies T2 implies T1. Okay? And here we have a lemma for other ways to formulate the definition of being normal and being regular. And so here's the lemma. So let X be T1, so X is regular if and only if for any element in X in any neighborhood U that contains X, there exists another neighborhood of X such that the closure is contained in the previous one. So to picture this, we have a set X, and we have a open set U, right? Set U, set U. Then we have another V, where it contains X, and this is like the closure of V is contained in U. Okay, so this is the thing. And now we have it is normal if and only for any A that is closed and any open set that contains A, then there is the open set that contains such that the closure is contained in U. So in normal is like for any closed set, so for any closed set A, right? And for any neighborhood, there exists another neighborhood of V such that the closure of V is contained entirely in U. Okay, so this is the picture here. And let's just prove them. Okay, let's shall we prove it. Okay, so let's prove A first. So for this forward direction, given the regularity of X, right, and for any X and U like contains X, then we can let B the closed set X minus U, right? So for this closed set by regularity, right, we can separate X and the closed set B, right? Because B does not because X is not in B, right? X is in U and B is the complement, so X is definitely not in B, right? So by regularity, we can separate them. And the claim is that this V, the closure of this V, is contained in this U. Okay? And to verify this, U is equal to X minus B, right? Because X minus U is equal to B, so X minus B will be equal to U, right? So we want to show this. Well, it suffices to show that the closure of V and B are disjoint, right? If this is true, it will imply this is true. So we want to show this is true, and indeed this is true, right? Suppose it is not empty. Suppose you can find an element, but Y is in V bar and is also in B. Is in B, remember, right? W is a neighborhood of Y. But this W and V are disjoint. So which means that we can find a neighborhood of Y such that it is disjoint with V, which implies that Y is not in V bar. Which we get a contradiction, right? We assume that isn't. So indeed, we show this direction. And now for the converse. Suppose we we have this condition. Suppose we have this condition for any neighborhood. If there's another neighborhood such that the closure is contained, we want to show that X is regular. Okay, so right, we have this initial condition. Let U equals to X minus B, which is definitely open because B is closed, and we can find a V neighborhood of X such that V bar is contained in U by assumption. Okay, so what we're gonna do now? What we're gonna do now is that V bar is closed, right? So the complement, it will be open, but X minus U is contained in X minus V bar because we have this. If this is true, it will imply this is true. Okay. Also, V in X minus V bar is contained in V intersect with X minus V, right? Because V is in V bar, so X minus V bar will be subset of X minus V, right? So exactly what we're saying here. And this is definitely empty set, so V and X minus V bar, they are disjoint. And also, V is a neighborhood of X such that, right, V is a neighborhood of X. And B is contained in this open set. And they are disjoint. So this is our pair. And in our case of normal spaces, we can really just replace the point X by a closed set A and the rest will be the same. We could verify it by ourselves, right? You can just repeat the proof here and here, right? You can just replace a point X by a closed set A. Okay, so we have our lemma of another formulation of closed, not regular and normal spaces. Okay, so we're going to use this lemma to prove something, and the something is our theorem. Is that given X is regular, then any subspace is also regular, and the product of regular space is regular. Okay, so this will be our thing. All right, so let's prove it. Let's just prove this first. For a subspace, well, if X is T3, then X is T2. So Y will be T2, right? The subspace of Hausdorff space is Hausdorff. And Y is T1. So the first condition is satisfied. Now let's separate a point in a closed set such that it's not in B. Okay. B is closed in Y. So the closure of B and Y is equal to B, right? X is not in B, then X will not be inside B bar, right? Because if X is in B bar, we have X and Y, right? So that will imply that X is in B, right? So X cannot be in B bar. Okay, now keep going. Because, well, this is a closed set in X, and X is not in here. So by the regularity of our big space X, we can separate X and B bar, right, by UV. And UV are disjoint, the intersect Y won't change anything, it will still be disjoint. And also X is in U intersect Y. And B will be equal to B bar intersect Y contained in V intersect Y. So this is the thing here. The key point is like B closed in Y, then the closure of B and Y will be contained in B. Right, the closure of B and Y. This is the closure of B and X, right? And from here, we can use the regularity of our big space, and we separate them. And then we intersect with B again, right? We still have our desired condition. So we're done with the subspaces. Now we're gonna prove with products. Okay, so the family of regular spaces, right? We know that if for the family of T3 spaces, then it is a family of T2 spaces. Then the product will be a T2 space, which is T1. So the first condition is satisfied. Now we use lemma to prove that this is T3. So what we're gonna do, pick a point X and here, And for any u neighborhood of x, right? For any u neighborhood of x, then will contain a basis element, right? Such that it is in the basis and subset of u. Now we analyze this basis, which means that for any alpha, we can pick this x in v alpha, and the closure of v alpha is in u alpha, because this is a family of regular spaces. X is in this, which means that each x alpha is in u alpha, right? Each x alpha is in u alpha. And then we apply the regularity of each x alpha, right? Which gives, by lemma, we have this. Okay, well, there's only finality of u alpha will be equal to like a basis, right? For the rest, we just set v alpha equal to x alpha. Then this is a neighborhood of x, no doubt, right? It is a basis element, right? Contains x. Basis elements are open, so this is neighborhood of x. And by the theorem, we have this. So it is in the product topology lectures, right? Here's the theorem. In either box or product, we have this equality, and the proof is here. Okay, you can take a screenshot and take a look if you want. You can pause and take a look, and just come back here. So we have this equality, and each v bar is containing u, v bar alpha is containing u alpha. So we will have this, and right, this. So the closure, this is a neighborhood of x, and the closure of this neighborhood is containing u. So for any u neighborhood of x, this is another neighborhood such that the closure is containing u. So by lemma, this is T3, okay? And in fact, we don't have the similar theorem for T4. And yeah, we can't have the above thing. We can't have this T4. No. Okay? Just to let you know. And yeah, this is really a sweet and short lecture on separation axioms, just like definitions. Okay? And for next time, we're gonna specifically discuss on normal spaces, like under what condition a topological space is a normal space. Okay? So I'll see you guys next time. Bye bye.